The next topic we need to tackle is the concept called improper intervals. Now, improper intervals could be improper for one of two reasons. First, let's look at the definition of a definite integral that we learned in Calculus 1 with the fundamental theorem of calculus. So, in the fundamental theorem of calculus, it said if we have this definite integral from a to b of f of x dx, rather than use the limit of a summation approach to evaluating this definite integral, which is the initial way you start to look at definite integrals, we instead learned the fundamental theorem of calculus, which said we could find the antiderivative, which we'll call capital F, and evaluate it at b, evaluate it at a, and then take their difference. And this has been the standard way you've done definite integrals since you learned that fundamental theorem. Now, there are two criteria in that fundamental theorem for this to apply. One, it requires that a to b, the interval a to b, be a finite interval, okay? Which sounds pretty standard, something we've seen all along, but it is a requirement. The second requirement is that the function f here in the integral, lowercase f, must be continuous on the entire interval from a to b. And so if one of these two things does not happen, that would cause an integral to be improper, but would also force us to not be able to use the fundamental theorem of calculus. And so in this section, we're going to look at integrals that don't satisfy those requirements and how we're going to be able to still evaluate the definite integral in hopes to try and use the fundamental theorem, because we know that it's fairly easy to use. And we'll do that through using limits, essentially. But again, this is the concept of an improper integral. So we always look to an example, and then we'll go from there. So let's look at the first scenario, okay? The first scenario where the interval is not finite, okay? That's what we're going to be looking for. We'll hold off on this continuity part for a little bit. So we look at the idea of what if the interval is not finite, okay? What if we were doing the integral from 1 to infinity of 1 over x squared dx, in which case the interval is 1 to infinity. That's the interval we're trying to integrate the function over. If we were to look at that graphically, it would look like this area, where here is the curve, 1 over x squared, okay? That's only a piece of it, but it's only the piece we need. And we're looking at it from 1 all the way down to infinity, so bounded by the x-axis and all the way down, okay? So we're trying to find essentially that area by integration. Now, one thing you know, and you know this from your study of functions and horizontal asymptotes from algebra and pre-calc, is that right here, this function never touches the x-axis, right? The function will continually, if you were to blow it up, the function will continually get closer and closer to this x-axis. This distance here would get smaller and smaller, but the function never touches the x-axis, the horizontal asymptote there. And so we're trying to find this area that technically goes on forever. Okay? I mean, this area never gets cut off because we're going all the way down to infinity on the x-axis, and this function here never touches the x-axis. So how are we going to go find that area? Well, one person might say, well, if the area goes on forever, then if this integral represents the area, it should be infinite. That's actually not the case, though. So how are we going to do this? Well, we want to try and apply this fundamental theorem here. But the fundamental theorem only applies if the interval is finite. So what we're going to do is we're going to say, well, this is the problem. What we're going to do is take that problem out. And we're going to say, well, let's do the integral from 1 to b of 1 over x squared dx, where we let b be some constant value here. Okay, so pick some random value b. And I can do the integral from 1 to b, so I can find this area here. Okay? And then let's say b is here now. And let's do the integral from 1 to b now. And we'll find that area. And then let's move b down a little bit further and say let's find the integral from 1 to b now. And what are we doing? We're letting b slide its way down towards infinity. So if I do the integral from 1 to b of 1 over x squared dx, and let's let b be 10, I could then figure out what the answer for this integral is. And then what I can do is I say let's let b be 100, and I could figure out what the answer is. Why? Because it would be a finite interval, and I can very well do this. Then let's let b be 1,000, okay? And keep doing this. And look at the answers I'm getting. What is the area for this particular b value? What is the area for this b value? What is the area for this b value? And the idea here is these areas should be approaching something. Whether that something is a finite value or an infinite value, these areas should get closer and closer to the actual area I'm looking for. And so if we do the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx, that will be exactly what I'm asking you to do here. Okay? Rather than do multiple integrals and look at the answers I'm going to get for different b values, if I just do the integral from 1 to b and leave b general b, and then after I do that integral, let b go to infinity with a limit, that should give me the answer for this integral. So if you notice, this is how we're going to get this thing done is essentially what I just explained, and you'll see how it's done in practice. So let's do the integral. So we have the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. And so that's going to give me the limit as b goes to infinity of, well, the integral of 1 over x squared. X to the negative 2 would be how I'd have to write this. So the integral of x to the negative 2 would be negative 1 over x between 1 and b. I would then plug in b and 1 and subtract, and I can do that. I can apply this fundamental theorem to this because we're calling b a finite value for right now. Okay? And so the limit as b goes to infinity of negative 1 over b plus 1 over 1. Okay, I'm just plugging in b and plugging in 1 and subtracting, applying my fundamental theorem. And now, here, this is where we're going to say, all right, well, the integration is now done. This is the answer we get. Now let's let b go to infinity. What I could do is I could say, okay, let's let b be 10. What kind of answer do we get? What's the area going to be? Let's let b be 100. Okay, what's the area going to be? Let's let b be 1,000. What's the area going to be? I could do that for this piece right here. And then I can look at all the corresponding areas and say, well, those areas look like they're getting closer and closer and closer to some value. So that's ultimately what this is going to do. But rather than do that, that's exactly what limits do. So I could just evaluate this thing as b goes to infinity. Well, if b goes to infinity, the denominator is going towards infinity, which means this whole fraction is going to go to 0. This is just a constant, which stays a constant, so 0 plus 1, and therefore the answer is 1. And so the areas, as b goes further and further down towards infinity, and I look at these areas, the area actually gets closer and closer and closer to 1. Yes, the area goes on forever, but the area is not infinite. And so this is going to be a big question we're going to tackle over the remainder of the semester when we get into the concept of sequences and series, is if I look at something that goes on forever and ever and ever, okay, and we're going to do it through a series of adding terms after term after term after term, and I don't ever stop adding, I keep adding and adding and adding forever, do the areas, do those sums go to infinity, or do they become a finite value? And in this case, this one is finite, but it's not always going to be finite. And so we need to look at a couple of examples. But This is the concept of an improper integral. So we break it into 3 scenarios here. Scenario 1 is the one we just dealt with, where we're working with an interval from a to infinity. So infinity is on the right-hand end of the interval, the top limit of your integral, in which case that is an issue, right? For us to apply the fundamental theorem, we have to take infinity out. So what I'll do is I'll replace infinity with b, and I can do the integral from a to b of f of x dx using the fundamental theorem. After I integrate, then I'll let b go to infinity by applying this limit. And this is how we can basically take an improper integral and apply the fundamental theorem to it. Scenario 2 is infinity's on the lower end, which would mean it would have to be negative infinity. So the interval from negative infinity to b. So that's the lower limit of our integration. We basically do the same thing. We'll replace that infinity with some constant. Let's call it a. We could do the integral from a to b of f of x dx, in which case then we can do the limit as a goes to negative infinity, thus allowing us to integrate. Scenario 3, we got infinity on both ends. So we're doing the interval from negative infinity all the way up to positive infinity. So it's the lower limit and the upper limit of integration. So how are we going to do this? Well, we're assuming that we're continuous on the entire interval. The second reason for being improper is discontinuity. We're going to ignore that for right now. So we're assuming we're continuous on this entire interval. And so here would be a picture of something that I'm describing. So think of maybe something like this bell curve, sometimes called the bump function, where it has a horizontal asymptote on either end. And let's say I want to find the area inside this. Okay? And in which case, if this is my function, it would be the integral from negative infinity to positive infinity of f of x dx. All right. What we could do is we could say, all right, well, if the function is continuous through the entire interval, let's cut it some random place. Let's call it C. Okay? And we can look at this area over here separate from this area over here. And this area would be from some constant to infinity. This area would be from negative infinity up to some constant, in which case, if I find these two areas, I could then add them together, and that would give me the total area. So I'm going to split it at some random location C, and I'll do the integral from negative infinity to C of f of x dx, which will be able to be evaluated using this method. And then I can do that added to the integral from C to infinity of f of x dx, in which case that would be evaluated using this method, with the upper limit being infinite. And then, once I evaluate both of those, I could figure out what the entire integral would work towards. C can be any real number. Doesn't matter where you split it. Usually I try and say, let's split it someplace convenient. You know, I don't want to split it at, I don't know, say square root of 7. If square root of 7 is not a convenient value to split at, usually 0, 1, pi. These will all be things that could be convenient to plug it in, because eventually you're going to have to plug this into the antiderivative when you evaluate it. So pick something easy, but since it's continuous everywhere, you can split it at any real number. All right. Now, one thing we know about limits is that limits exist and limits don't exist. You have two options there, right? Not every limit's going to exist. Not every limit's going to give you a value, right? Sometimes limits don't exist. And ultimately what we're doing is we're taking the limit of something, okay? And we're trying to figure out what the answer is in the end after we evaluate the limit. And it's possible that that limit does not exist. For a limit to exist, remember, it has to be equal to a finite value, okay? A limit has to be equal to a finite value for it to exist. If you get infinity, that technically does not exist. Okay? So the idea here is for this improper integral to exist, the limit has to exist, in which case what we say is that the integral converges if the limit exists. Okay? And if the limit doesn't exist, we say the interval diverges. Now, in this third case here, we get two different integrals for this single integral. So in order for this main integral to converge or diverge, both of these two separate integrals have to either converge. For this to converge, okay, let me rephrase that. In order for this integral to converge, okay, both of these integrals here have to converge. If just one of these two integrals diverges, if one of these two limits diverges, then this whole integral will diverge. Okay? So, in order for the main integral to converge, both of the resulting integrals have to converge. If just one of the resulting integrals diverges, then the entire main integral diverges. Let's look at a couple examples. All right, so here, these are very easy to spot that you're dealing with an improper integral because automatically you see infinity as one of the limits of integration, or both the limits of integration for that matter. So you know right away you're dealing with an improper integral of this type. So here we go. First thing we want to do is we want to make this integral proper. So we're going to do the integral from 1 to b instead of 1 to infinity of dx over x. But then we have to do the limit as b goes to infinity. And it's important that you write all that down. I mean, without that, it doesn't make any sense as to what's going on here. And so now that we have it made set up proper, so we're going to then do the integration. So we have the limit as b goes to infinity of the integral of dx over x. Well, that's your basic logarithm integral, log x between 1 and b. We're then going to plug in b and plug in 1. Subtract, so we're going to get the limit as b goes to infinity of log of b minus log of 1. Log of 1, you should know, is 0. Okay. So here's now time to evaluate this function as b goes to infinity. This is the only thing that has a b in it. So then you got to think of what's the limit as b goes to infinity of log of b. Well, if you know what the graph of the logarithm looks like, and we all should, we should easily be able to see that if that's what a logarithmic graph looks like as b goes to infinity, or x, or whatever you want to call this axis here, the function itself is going towards infinity. And so you would get infinity minus 0 over infinity. Well, when you get a limit to equal infinity, what does that tell you? It basically tells you the limit doesn't exist. And so we would say then, therefore, which you could simply just use this symbol instead if you wanted to, therefore, the integral diverges. And that's it. All right, here's another one. Again, easy to spot. Got infinity right there. So I'll correct it. I'll do the integral from 0 to b of e to the negative x dx. And then I'll do the limit as b goes to infinity. And then we're going to do the limit as b goes to infinity of the integral for e to the negative x. That's negative e to the negative x, pretty easy integration from 0 to b. I'll plug in my b and I plug in my 0, so I have the limit as b goes to infinity of negative e to the negative b plus e to the 0. E to the 0, you should know, is 1, because anything to the 0 is 1, so that's a 1. So now it's time to evaluate this as b goes to infinity. Okay. So if b is going to infinity, what am I going to do here? Well, I'm going to rewrite this as b goes to infinity. I'm going to write this as negative 1 over e to the b. I think you might see the answer better if I wrote it like that. As b goes to infinity here, e to the b, this whole piece, also goes to infinity. So if the denominator of this fraction is going to infinity, but the numerator is staying constant 1, this whole fraction, you should all know, goes to 0. And therefore, this will be 0 plus, this is the constant, so it's just going to stay 1 no matter what's happening with b. And so the limit ends up equaling 1. So we could say, therefore, the integral converges to 1. That's it. Okay, the limit exists, therefore the integral exists, and it converges to that value. All right, here's yet another one. Again, pretty easy. Spot it. That's definitely improper because of that infinity. So we'll correct it. 0 to b, 1 over x squared plus 1 dx. Then do the limit as b goes to infinity. So now that it's set up properly, now it's time to integrate. So we still have this limit as b goes to infinity. Yes, you have to keep writing it until you evaluate the limit. Otherwise, it doesn't make any sense. So then we'll do the integral of 1 over x squared plus 1. You should recognize that as your arctan integral. Arctan of x between 0 and b. So then I have the limit as b goes to infinity of the arctan of b minus the arctan of 0. Everyone should know that the arctan of 0 is 0. Okay. So here's the arctan of b as b goes to infinity, and now the question is, well, what's going on here? What is the limit as b goes to infinity of the arctan of b? If you can look at the graph of these functions, that tends to help you find what the limit value is. Think about the arctan graph. The arctan graph has two horizontal asymptotes and looks like this in between. So as x or b or whatever goes to infinity, the y value is getting closer and closer to that horizontal asymptote, which is located at pi halves. This lower one is located at minus pi halves. So if we're going to negative infinity, we get closer and closer to negative pi halves. So knowing that, you can see that the limit as b goes to infinity of arctan of b should approach pi halves. And remember, this is 0, so pi halves is the answer for the limit, and therefore the answer for the integral. So therefore, the integral converges to pi halves. All right, here's another one. Again, improper. All these ones have the upper limit is the improper part, the infinite part. It really doesn't matter whether it's the upper or the lower. It doesn't change how you do things, other than whether you go into negative infinity or positive infinity and it's the bottom or the top. So in this case, it's 1 to b of 1 minus x e to the negative x dx. We're going to do the limit as b goes to infinity. So now that's set up, we have to think about how we're going to do this integration. I could pull that off to the side and say, all right, well, if I'm going to do this integral of 1 minus x e to the minus x, I got to come up with the antiderivative for that first, and then I can fill it into this problem as far as the limit as b goes to infinity, etc. Well, the way you're going to do this integral is by parts. Okay? If u equals 1 minus x, dv equals e to the negative x, du is going to be negative dx, and v is going to be negative e to the negative x. Okay? So in which case, u times v would be 1 minus x times negative e to the negative x, minus the integral of v du, which is this times this, and then minus, so I have three negatives here ultimately, that, and that, so it's going to stay negative. So e to the negative x dx. This negative here, I'm going to distribute in here, which is just going to switch the sign around here. So instead of 1 minus x, x minus 1, e to the negative x, and this will become plus e to the negative x, because I'll get an extra negative out of the integration. And so there's my integral. So if I fill that into this problem, I have the limit as b goes to infinity of x minus 1. I'm going to write this over e to the x. It's times e to the negative x, but I'll write over e to the x, plus 1 over e to the x between 1 and b. All right, so then I'm going to plug in b and plug in 1, and I get the limit as b goes to infinity of b minus 1 over e to the b plus 1 over e to the b minus, when I plug 1 in, if I plug 1 in here, I'm going to get 1 minus 1, which is 0 over e to the first, so that'll just be 0, minus, if I plug 1 in here, I'm going to get 1 over e. Now, all this is just constant, so it doesn't matter what's happening with b, this is just going to stay constant. This is what you need to concern yourself with when it comes to the limit. Those are the pieces that have b's in them. So as b goes to infinity, what happens? Well, if b goes to infinity, we can look at these separately. Let's look at this fraction here. As b goes to infinity, the numerator is going to go to infinity, the denominator is going to go to infinity. So we have an infinity over infinity limit. How are we going to handle that? Well, that's where L'Hopital's rule is going to come in. Over here, we have 1 over e to the b, and as b goes to infinity, the denominator is going to go to infinity, but the numerator in this case stays 1, and so this whole fraction is going to go to 0. So we need to do L'Hopital's rule here. We know this is going to go to 0, this is going to stay 0, and this is going to stay 1 over e. And so if we do this limit as b goes to infinity of the L'Hopital's rule evaluation of this limit, we would get the derivative of the numerator, which would just be 1, the derivative of the denominator, which would be e to the b. Remember, this one is 0, this is 0, this is 1 over e. All that is constant right now, so it's just this one we're working with. Well, this is the same integral we just did. We know that this one's going to go to 0 for the same reason this one over here did. And so ultimately, what do we get? We get negative 1. Let's write something you can see. Negative 1 over e is the answer. And we could say, therefore, the integral converges to negative 1 over e. And it's negative. It's okay that it's negative. We tried to explain a little bit about these improper integrals by looking at areas, but not every area does actually evaluate as an integral. Not every integral is an area itself, or does it represent an area? So you can get a negative answer. That's totally fine. And any integration technique might need to be used here at this point, because we're just evaluating integrals. We are making them proper and we're evaluating them. So yes, you might need integration by parts to get this done. Yes, you might need L'Hopital's rule to get some of these limits done. All these things we've learned along the way could come into play in one of these problems. All right, so here we got one where we have both limits of integration are infinite. Notice that this function right here is continuous everywhere. It's a fraction. The denominator of this fraction will never equal 0, because this piece will never equal negative 1, and therefore you'll never get 0 in the denominator. So if it's continuous everywhere, what we can do is we can split this interval any place we want. So I'm going to choose 0. And I can always go back and change that if it looks like something might be a better fit for my limits of integration in terms of plugging into the antiderivative. I'll start with 0. So I'll do the integral from negative infinity to 0 of e to the x over 1 plus e to the 2x dx, plus then the integral from 0 to infinity of e to the x over 1 plus e to the 2x dx. And again, I could always just go back and change that to a 1 or a 5 or whatever I want to do. But we'll start with 0. 0 is usually an easy value to work with. We're still doing the integral from negative infinity to positive infinity, just in 2 parts. All right, so the first one has an infinity on the bottom limit. That's an issue. The second one has an infinity on the upper limit. So I'm going to have to do 2 different limits here. So first one, I'm going to do the limit as a approaches negative infinity of the integral from a to 0 of e to the x over 1 plus e to the 2x dx. plus the next one's going to be the limit as b goes to positive infinity of the integral from 0 to b of e to the x over 1 plus e to the 2x. And I'm using a and b. This variable that we're using here and here is just a dummy variable. It doesn't matter what you call it. You just have to let that variable go to negative infinity and let that variable go to positive infinity in either case. So call it whatever you want. Sometimes you'll call it a t. It doesn't matter. All right. So now it's time to integrate. And we have two integrals here, but they're the same integral. So it's not like we have to do two separate integrals. Once we evaluate the integral, we're going to use it here and here. So now we got to think about, all right, let's do some scratch work here. E to the x over 1 plus e to the 2x dx, and how we're going to integrate that. Well, the key is that e to the 2x is e to the x squared. We've seen this before. So if I let u equal e to the x, du is e to the x dx, and let's say a equals 1, then what happens? This is u squared, this is a squared, and here is my du. So I end up with the integral of du over a squared plus u squared. And you should recognize that as our arctan integral, 1 over a arctan of u over a, where a is 1 and u is e to the x. So then if I fill that in to this problem, I get the limit as a goes to negative infinity of arctan of e to the x between a and 0 plus the limit as b goes to infinity of arctan of e to the x between 0 and b. All right, let's take care of this to get rid of this. All right, now we're going to plug in 0. We're going to plug in a. So we have the limit as a goes to negative infinity of arctan of e to the 0, which would be 1, minus arctan of e to the a, plus, I'm going to run out of room, I'm sure, the limit as b goes to positive infinity of arctan of e to the b minus arctan of e to the 0, and e to the 0 again is 1. So it looks like 0 should be pretty easy to work with, so I'm going to keep it at 0. But if you get to this point, you go, oh, I'm going to plug in 0 here, and that's not going to be so easy to do. And go, well, maybe it would be easier if this was a pi instead of a 0. Or maybe it would be easier if it was a 1 instead. In which case, then, you would just have to go back and change all those values to something else. 0 tends to be easiest. All right, so let's look at this. Arctan of 1, you should know, is pi fourths. Okay, so that's pi fourths, that's pi fourths. Okay. E to the a, arctan of e to the a. Let's think about this. A is going to negative infinity. And so e to something that goes to negative infinity actually gets closer and closer and closer to what? Well, think about this. Okay? This is what e to the x looks like. Okay? This is what e to the a or e to the x looks like. As we go to negative infinity, the function itself is getting closer and closer and closer to 0. As we go to positive infinity, which is down this end, the function is going to infinity. And so that's how we're going to look at doing the two limits we need to do, this one and this one. And so for the first one, this is getting closer and closer and closer to 0. And so what do we get? We get pi fourths minus the arctan of something that gets close to 0. Well, then the arctan is going to get closer and closer to 0 as well. Plus the limit as b goes to infinity. Well, I don't have to write that again. This one. We know that this is going to get closer and closer and closer to infinity. And so then the arctan of something that gets close to infinity should get closer and closer to pi halves. And that's because of what we showed earlier, which was we have that arctan graph. As it go close to infinity, the arctan gets closer and closer to pi halves. And this is going to stay pi fourths. So what do we end up with? Pi fourths plus pi halves minus pi fourths, we get pi halves overall. And so the integral converges to pi halves. Now notice, we have two separate integrals here, right? These two separate integrals. This is the answer for the first integral. This is the answer for the second integral. Both of them converged, okay? The first one converges to pi fourths. The second one is pi halves minus pi fourths, so actually the second one converges to pi fourths as well. But both of these integrals converge. So that means this integral right here also converges, and it converges to whatever that sum is, which happens to be pi halves. If one of these two diverged, right? Remember, this is the answer here, and this is the answer here. If one of these diverged, then this entire integral would diverge. So just keep that in mind. Now we have to tackle the other reason why an integral might be improper, and that's the discontinuity one. This isn't all that much more difficult than the first one we did, and now that we have that knowledge of how we handle the first improper, which is the infinite limit of integration, it will make this even easier. So we look at it in three scenarios. Let's look at the first scenario, and that is that we have a function that's continuous on an interval a to b, except for the right-hand end of the interval, the uppermost part of the interval. There's a discontinuity at b, okay? So the very end of the integral, that is the issue. Graphically, it would look something like this. We have some function that's totally fine from a all the way up till we get to b, but there's this vertical asymptote here at b. So the vertical asymptote at b is that discontinuity, right? It's this infinite discontinuity. So what we're going to do is we're going to say, all right, well, let's pick some random value t that is inside this interval. So it would have to be on the left-hand side of b. And let's call that value t, and let's do the integral from a to t. Well, that is a perfectly fine integral right there. There's no problems with that because t is not a discontinuity. T is inside the interval, and it is continuous everywhere inside the integral. And I can do the integral from a to t of f of x dx. But that's ultimately not what we want. We want to do from a to b. So what are we going to do? Well, what we're going to do here is t is on the left-hand side of b. We're going to let t go to b, but it's only going to be from one side, in which case it's going to be from the left-hand side. And so if we do the limit as t goes to b from the left of the integral from a to t, that will then allow t to approach b, we'll get closer and closer to b, and we'll figure out what the integral from a to b actually is. So again, a trick to kind of make the integral proper first from a to t, and then let t go to the discontinuity. We could do the same thing on the other end. Let's say we have a function that's continuous on the interval from a to b, except it's not continuous at the end. In this case, the lower end is an infinite discontinuity, so a, it's down here. So in which case, we'll pick some random value t inside this interval, which means that t has to be on the right-hand side of a. If it's going to be inside the interval, t is on the right-hand side. We do the integral from from t to b, and all this is totally fine. We could find that area if we needed to, right? So we do the integral from t to b of f of x dx, and then we're going to let t go to a, but it has to only go to a from one side. Since t is on the right-hand side, t is going to approach a from the right-hand side, so a from the right. So we do the one-sided limit, t approaches a from the right, of this integral from t to b. So notice that these are one-sided limits because of the way that t is oriented, being inside the interval and only approaching the discontinuity from one end or the other. Third scenario is that discontinuity is inside the interval. So we have a vertical asymptote inside the interval. So we have the function is doing, we're working with the function from a to b. It's continuous everywhere in a to b except somewhere inside we'll call c. So what we're going to do here is say, well, c is the problem. So we'll split this at c. We're not going to split this at some random location. We have to split this at the discontinuity. And if we split this at the discontinuity, we could do the interval from a to c, in which case we have the upper limit of that interval is the issue, which essentially takes us to this scenario. And then we have the integral from c to b, in which case the lower limit is the issue. And we have this integral, which essentially takes us into this scenario. And we would work with each one of these separate integrals by essentially method 1 or method 2. So we turn a discontinuity in the middle of the integral into endpoint discontinuity by splitting it at that particular location. Again, ultimately, we're going to be doing a limit, and limits can exist or not exist. So the improper integral will converge if the limit exists, and it will diverge if the limit doesn't exist. In case number 3, since we take this one integral and we write it as two separate integrals, both of these integrals have to converge for the single integral to converge. If just one of these two integrals diverges, then this entire first integral diverges. A lot of the same things going on here. But the key is we use limits to help us evaluate the integral and use the fundamental theorem by taking the problem value out, replacing it with some random value t or c or whatever we want to call it, and then do the limit as we approach that value. So here's an example. The problem you're going to have with these integrals is recognizing that they're improper. It's not as obvious to recognize that these are improper integrals as was the previous ones where you saw infinity in one of your limits of integration. And so when you look at this, this looks like just the same old integral you've been dealing with since Calculus 1. But if you look closer at the function that we're working with, the function that we're working with in this integral is 1 over the cube root of x. That function is discontinuous at x equals 0. X equals 0 just so happens to be the lower limit in the interval of integration. And so therefore this is an improper integral. So when you've done definite integrals up to this point, you've never really thought too much about the interval you were working with. You just knew in the end you would have to plug the values in and subtract. But now every single definite integral you do, you have to think about the continuity of the function over that interval. In this case, we have a discontinuity at the end of the interval. If I gave you this integral from 1 to 2 of dx over the cube root of x, that is not an improper integral, in that 0 is not in this interval anywhere, and therefore this function is continuous on that entire interval, even the endpoints, and this is just a plain old integral you would have done back in Calc 1. But it looks very similar to this one, except for that slight change in the interval in which we're integrating over. So that's something you're going to have to pay very close attention to from now on. Every integral you do from here on out for the rest of your life, you have to be concerned with the interval of integration and whether or not my function I'm integrating is continuous over the entire interval. So in this case, it's not. So we're going to correct it. So we'll do the limit as, let's say, t goes to 0. We got to decide from the left or from the right. So if you think about it, we have the interval from 0 to 1. This is the interval we're working with. This is the interval. I have to pick a t inside the interval, and that t has to approach the problem point, which is 0. So in this case, I'm approaching it from the right of the integral from t to 1 of, I'm going to rewrite this as x to the negative 1/3 dx. I have to write in power notation anyway to integrate it, so I might as well just do it now. Cube root of x is 1/3. It's in the denominator, so now it's negative 1/3. All right, so now that we're all set to go, integration is easy here. So we have the limit as t approaches 0 from the right of the integral. Add 1 to the exponent, divide by. So what are you going to get? You're going to get x to the 1/3 times 3. So 3x to the, x to the 2/3 times 3/2. Okay. Between t and 1. So then I have the limit as t goes to 0 from the right of plug 1 in. I'm going to get 3/2 times 1 to the 2/3 minus 3/2 times t to the 2/3. This is just a constant. This has got t in it. T is going to 0 from the right. Well, whether it's going to 0 from the right or from the left doesn't really matter necessarily, because this is going to go to 0, which makes this whole thing 0. So we end up with 3/2 as our answer. And therefore, the integral converges to 3/2. But the tricky thing is you have to watch out for the interval. Because again, if I did the interval from 1 to 2 of the exact same function, cube root of x, I wouldn't have to do anything with limits. I wouldn't have to replace any of this with a t. I would just go straight ahead and integrate it. So be careful. Again, take a look at this one. Just looks like a normal old integral, but when you look at the function f of x equals 1 over x cubed, this is discontinuous at x equals 0, which again is one of the endpoints of this interval. So you have to be concerned with this, in which case it makes this an improper integral. So what are we going to do? We're going to replace the 0 with any variable you want. Let's just say t to 2 of, I'm going to write this as x to the negative 3 dx so that it makes it easier to integrate. And then I'm going to do the limit as t goes to 0 from the right again. Why from the right? Again, think of it as an interval. Here's 0, here's 2. T has to be inside the interval. So here's your t. So if t is inside the interval, which is all in here, t would have to approach 0 from the right. It's very important. Sometimes left-hand limits, right-hand limits are the same as a full limit. Sometimes they're not. So you have to make sure you approach from the appropriate side. All right, so now it's all set to go. Pretty easy to integrate. Here's the limit as t approaches 0 from the right. The integral would be add 1, divide by. So what do we get? We get negative 1/2 x to the negative 2 between t and 2. So I have the limit as t approaches 0 from the right of negative 1/2 times 1 over 2 squared minus 1 over t squared. So as far as t going to 0 goes, this one right here is not affected by it. This is the problem. Now t is going to 0 from the right. T is not 0. T is approaching 0. Because you would look at this and go, well, the denominator can't be 0, so we can't do it. But no, the denominator is approaching 0. So if this denominator is approaching 0, what's happening to the whole fraction? Well, what's happening to the whole fraction is that it's going to keep getting bigger and bigger. As the denominator gets smaller and gets closer to 0, the whole fraction gets bigger. So we have this negative 1/2 times 1 over 4 minus infinity. all this really doesn't matter here. None of this makes sense. Well, it makes sense, but none of it matters in terms of the fact that we get infinity. So the answer is really just infinite, which tells me that the limit doesn't exist, which tells me that the original integral diverges. So therefore, the integral diverges. Okay. Now let's look at this one. It looks very similar to the last integral. The only difference is the interval in which we're integrating. In this case, -1 to 2, 0 is inside that interval. 0 is the problem for the function. But it's not on the end of the interval, it's inside. So first thing I'm going to do is I'm going to have to split it at that discontinuity, which is 0. So I'm going to go -1 to 0 of dx over x cubed plus 0 to 2 of dx over x cubed. Then I would have to do the limit as, let's say, a goes to 0 from the left, from -1 to a of dx over x cubed, plus the limit as b goes to 0 from the right of b to 2 of dx over x cubed, and then evaluate from there. Now, because we've already done this one, we just did it a second ago, we know that this one diverges. Well, if that's part of the larger integral, it's only one piece of the two different pieces that make up this larger integral. If one of them diverges, then the integral from -1 to 2 of dx over x cubed diverges as well. And we don't have to do all the work all over again because this work was just done a second ago. This is x cubed. If I give you the integral from 3 to 7 of dx over x cubed, you wouldn't have to go through any of this because this is just a standard old proper integral. 0 is nowhere in this interval. It's not on the end. It's not in the middle. This is completely fine. The function is continuous over the interval. You would just integrate as normal. But when you have a discontinuity, that's what you have to worry about. And that's what you're going to have the hardest time recognizing. Is do I have a discontinuity? Because you're going to have to just train yourself. All right, now we have this one. Be careful here. First off, look at the function. The function we're working with is 1 over the square root of x times x plus 1. This is discontinuous two places. When x equals -1, that's when this will be 0, and when x equals 0, that's when this will be 0. Also, x has to be greater than 0 for the square root to work out. So since it can't equal 0 and it can't be negative, x has to be strictly greater than 0, and it can't equal any of these, but these are all going to be less than 0. So the only x's we can work with here are x's greater than 0 in this function. Well, look at the interval. The interval is 0 to infinity, which is largely greater than 0 except for this endpoint, which is 0. So that endpoint is a problem. That's a discontinuity. But after that, we're okay, all the way until we get to the upper limit, which is an infinite limit of integration, which is also a problem. So this has two issues with it. Two issues. We have a discontinuity and we have an infinite limit of integration. So to fix that, we're going to have to take this and split it apart. Remember, it's continuous between 0 and infinity, so we can split it anywhere we want. So what I'm going to do is I'm going to go, say, 0 to 1 of dx over x square root of x times x plus 1, plus 1 to infinity of dx over the square root of x times x plus 1. Now I do this so that I can separate the two issues I'm having. This first integral has the discontinuity on the lower limit, and the second interval has the upper limit being an infinite value. Rather than trying to deal with both at the same time, if I separate them out, it makes it a lot easier for me. And I chose 1 to be the place where I split because 1's an easy number to work with. It's just randomly pick 1. I can pick 2, I can pick square root of 7, I can pick whatever I want. So I went with 1. So to fix the first improper component is to get rid of the 0. So I'm going to do the limit as t approaches 0 from the right of the integral between t and 1. Again, from the right, because I have 0 to 1 is my interval. T is going to be inside that interval, and t would have to approach 0, in this case from the right. Okay? And then I still have dx over the square root of x times x plus 1. Plus, the next one I'm going to have the limit as, let's say, b goes to infinity of the integral from 1 to b of dx over the square root of x times x plus 1. So now both of these integrals are ready to go. Now I have to worry about how do I even do this integration. So we got to think about this integral. The integral of dx over the square root of x times x plus 1. How we're going to go about this. Well, here's the trick to this. The square root of x squared is the same thing as x. So that's here. Okay? Not true. The square root of x squared is actually equal to the absolute value of x. And the absolute value of x is equal to x when x is greater than or equal to 0, and negative x when x is less than 0, just a definition of absolute value. But remember, we're working with x's that are greater than or equal to 0, so square root of x squared actually just equals x. Got to be precise with it, really should show that. It matters. If we were dealing with a different interval, it would matter. So anyway, get rid of all that. The whole point is the square root of x squared is equal to x here. And so what we're going to say is that if u equals the square root of x, then this is u squared. And then du would be the derivative. Remember, square root of x is x to the 1/2. So that would be 1/2 x to the minus 1/2 dx. If I move this 2 over to here, and I rewrite this as dx over the square root of x, that's exactly what I'm looking at here. So what does this turn into? It turns into 2 du, that's this piece, over u squared, plus, let's say, a equals 1, a squared. So then what do I end up with here? I end up with 2 times 1 over a arctan u over a. What was a? 1, so 2 times 1 over 1 is just 2 arctan of u over a. U was x to the 1/2, so x to the 1/2 over 1. That's the answer for my integral. All right, so now we got to insert that in for the integration here and here. So let's space this out. So we have the limit as t approaches 0 from the right of arctan of x to the 1/2 between 1 and t, plus the limit as b goes to infinity of the two arctan x to the 1/2 between 1 and b. Okay. Now, something to note before we go any further. This one integral turned into these two separate integrals, which are going to give us this and this. If just one of these two does not exist when we eventually do the limit, if one of those two integrals diverges, this entire thing will diverge. Okay, keep that in mind. So we need both of these limits to exist for the original integral to converge. All right, so that we plug in t, we plug in 1. For the first one, we get the limit as t goes to 0 from the right of arctan of t to the 1/2 minus arctan of 1 to the 1/2, so just 1. We already said we know that's pi/4. Okay, so I just have to figure out what happens as t goes to 0 here, plus this other one, try not to run out of room, b goes to infinity of 2. I missed a 2 somewhere along the way over here. That's important. I need that 2. So I'm going to have a 2 there and there. I don't know why I missed a 2 there. 2 arctan of b to the 1/2 minus, right here, 2 arctan of 1. Okay? So, this is getting kind of messy, but let's look at this. T is going to 0 from the right. So t to the 1/2 is also going to go to 0. And if that goes to 0, the arctan of something that goes to 0 also goes to 0. And so for this whole big thing, as we take the limit, this whole one is just 0. This one is going to be minus 2 times pi fourths. That's this one. And so that's the first integral. That's what we're going to get. All right, so that one existed. That's what we end up with. Plus, now we go to the next one. As b goes to infinity here, b to the 1/2 also goes to infinity. And the arctan of something that goes to infinity goes to pi halves. We've said that before already in this lesson. So then we get 2 times pi halves minus, this one is, again, 2 times pi over 4. So what do we end up with here? What we end up with is, this is going to be minus pi halves, plus pi, so pi minus pi halves, we in the end get 0, which is okay, right? I mean, getting an answer of 0 is fine. That tells us the original integral, which is all the way back here, converges to 0. But this point of this problem was that there were 2 different issues here. There was improper because of the discontinuity. There was improper because of the infinite limit on the integration. We handle each one of them separately. Don't try and keep them in the same integral and do like 2 limits at once. You're not going to be able to get that done. Separate them out. Evaluate each one. If one of them doesn't exist, the whole thing diverges. Since both of them did exist, the whole thing does converge, and in this case converges to 0, and that's totally fine. All right, that brings us to this special type of improper integral. This is going to come up in a way when we talk about series. What we can do is we can look at this special type of improper integral, where it's the integral from 1 to infinity of dx over x to the p. We've done some of these already today. And the idea here is that this will converge or diverge purely based off of the power on the x. The interval has 1 from infinity. All this has to be pretty consistent. But the power on the x to the p, makes all the difference. What it says is that if the power is bigger than 1, it will converge, and it'll converge to 1 over p minus 1. And if the power is less than or equal to 1, it will diverge. Now we can quickly see that with a proof of this special type of integral, but let's just apply it to this integral right here. The integral from 1 to infinity of dx over x to the first. Well, if you look at that, that's going to automatically, by this, diverge. Why? Because p equals 1. And therefore it falls into this category. But why? Well, let's look at this. Let's look at the integral from 1 to infinity of dx over x to the p. First off, we have to do the limit as, say, b goes to infinity of the integral from 1 to b of dx over x to the p. Right. And what we're going to do is we're going to break this off into 2 scenarios. First scenario, p equals 1. Second scenario, p does not equal 1. Because the integration is very different. If p equals 1, we end up with the limit as b goes to infinity of the integral of 1 minus b of dx over x. in which case we would integrate using logarithms. If p doesn't equal 1, we have the limit as b goes to infinity of the integral from 1 to b of x to the negative p dx. We would just bring the power up, and we can use the power rule to do that integral when the power isn't 1. And so if we use each one, first let's look at the integral, the first one, with p equals 1. So we do the limit as b goes to infinity of the integral from 1 to b of dx over x. Okay? And we've seen this one, this is the example right here. We know it's going to diverge, but we also did this one earlier in the lesson, something very similar to it at least. And what are we going to do? We have the limit as b goes to infinity of log x between 1 and b. We're going to get the limit as b goes to infinity of log b minus log 1. Log 1 is 0, so it's all just based off of this log b as b goes to infinity. But the limit of log b as b goes to infinity goes to infinity. So we end up with infinity as the answer, therefore it diverges. Okay? So you see, when p equals 1, specifically this integral right here, you know it's going to diverge. But what about for the other p's? When p doesn't equal 1, we have to look at this. And so that's what we have to look at a little bit closer. And we're going to really have to determine what happens with this integral, and it's really going to determine whether p is less than 1 or p is greater than 1. When p is greater than 1 and when p is less than 1, this limit works out very, very differently. And that's why we get these two scenarios. So we want to do the limit as b goes to infinity of the integral from 1 to b of dx over x to the p where p doesn't equal 1. And so, like I said before, to do it, we need to look at it as, all right, the integral of x to the negative p dx is the integral we're going to need to talk about. We can do it that way because if p doesn't equal 1, it will simply be a power rule integral. So what are we going to do? We're going to add 1 and divide by that new power, which I'm going to write instead as x to the 1 minus p over 1 minus p instead of negative p plus 1. All right, so that's how the integration is going to go. So if I insert that back into here, I end up with the limit as b goes to infinity of, again, x to the 1 minus p over 1 minus p between 1 and b. So then what I'm going to do is I'm going to plug in b and plug in 1. This 1 minus p is a constant, so I'm going to write it like this. I'm going to do the limit as b goes to infinity of 1 over 1 minus p times b to the 1 minus p minus 1 to the 1 minus p. Okay. Remember, p doesn't equal 1. So that being said, neither of these exponents and this here, none of that is 0. All right. So now it comes into, well, we got to take the limit as b goes to infinity. The only b component to this whole thing is sitting right here. So when I look at the limit as b goes to infinity of b to the 1 minus p, and all I know is that p doesn't equal 1, I got to figure out what this is. Well, actually there's two scenarios here. One where p is greater than 1 and one where p is less than 1. Because that's going to affect this exponent. If p is greater than 1, then 1 minus p is negative. Okay? If p is less than 1, then 1 minus p is positive. And when it comes to an exponential function, which is what we're looking at here and taking the limit of, if we do it to if we have b to a negative exponent versus b to a positive exponent, and we look at each of those as b goes to infinity, we get a very different answer. think about these two functions, a to the negative x versus a to the x. Graphically, this one looks like this, and this one looks like this. So as we go to infinity, we get closer and closer to 0 with this function, the negative exponent, and we get closer and closer to infinity with the positive exponent 1. So this limit could equal two things. It could equal 0 when we have the negative exponent, and it can equal infinity when we have the positive exponent. Well, that makes a big difference here. Again, p is a constant, right? So then this is really just 1 to the p, 1 to the 1 minus p here. So it's 1 to a power, so ultimately that's just going to be 1. This is 1 over 1 minus p, that's just a constant. So what happens here makes all the difference. Okay, so what's going to happen is we're going to say, all right, well, if p is greater than 1, the answer for this limit ends up giving me 1 over 1 minus p times 0 minus 1. And when p is greater than 1, we get 1 over 1 minus p times infinity minus 1, which is really infinite here. And so in this scenario, we diverge. In this one, we converge with the original integral. In this case, we converge to this. And we could rewrite that as, negative 1 over 1 minus p, or we could also write it as 1 over p minus 1, just distribute the negative to the denominator. But we see, okay, when p equals 1, we diverge. When p is less than 1, we diverge. When p is greater than 1, we converge, and we converge to 1 over p minus 1. And so now we looked at that integral, and we noticed why it said what it said. It said, let's erase some of this and get some space, that if we do the integral from 1 to infinity of dx over x to the p, it equals 1 over p minus 1 when p is greater than 1, and it diverges when p is less than or equal to 1. It's because of what we just showed. So now, if you ever do one of these integrals, you don't actually have to do anything. We just showed what the answer will be based off of p, and you can use that. And we will use that when we do something with infinite series in the next unit that relates directly to this integral.